Dear learners, welcome to everyone. For today's session, let us start our PCA syllabus 4th year first semester subject, which is Instrumental Methods of Analysis. I am Divya Narla from the Department of Analysis, Aditya College of Pharmacy. So in this course of your final year B.Pharm program, particularly with the subject of Instrumental Methods of Analysis, the student will be able to understand these objectives of the course. So here are the course outcomes. So where the student will be able to understand the principles of spectroscopy, chromatography and electrophoretic techniques, and the student will be able to understand how the electromagnetic radiation will be interacting with the sample matter and what are the applications of such interaction of this matter with EMR with respect to drug analysis. And also the student will be able to understand the separation principles in chromatography as well as in the electrophoretic techniques, and how the separation process will be helping in the analysis of drug either in their bulk or in formulations or well as in their biological samples. And apart from this, the students will also be able to understand, or they will be to impart the knowledge regarding the instrumentation of various spectroscopic techniques as well as chromatographic techniques. And other than knowing a basic regarding the instrumentation of these various analytical techniques, they will also able to understand the various applications of each and every instrumental method relative to the qualitative and quantitative analysis of drugs. And the last objective and the most important objective of this course is that the students will be able to perform various quantitative and qualitative analysis of drugs using various analytical instruments. So here are the list of your topics which we will be dealing in our next sessions. So the unit 1 of this IMA subject will be dealing with the spectroscopic techniques, particularly with UV and visible spectroscopy, followed by fluorimetry. And the next unit, or the second unit, will be dealing with the IR spectroscopy, flame photometry, atomic absorption spectroscopy as well as with nephoturbidimetry. And in the third unit we will be discussing this chromatographic techniques, so where we will be understanding the principles of chromatography followed by a few topics of chromatography. So we will be studying the introduction to chromatography followed by column chromatography involving both adsorption as well as partition as the principle of separation, followed by thin layer chromatography and then paper chromatography, and also the basics of electrophoresis. And the unit 5 will be dealing with the sophisticated chromatographic techniques such as gas chromatography and high performance liquid chromatography. And unit 5 will be dealing with ion exchange chromatography, gel chromatography and affinity chromatography. So all these will be the various list of our topics which we will be discussing one by one in the next sessions. And now let us continue with this spectroscopic techniques, and before that we will be discussing the introduction regarding what is spectroscopy and what are the various basic terms which are applicable in the spectroscopic techniques. So let us continue with our unit 1, which is dealing with the spectroscopic technique. So in this we will be discussing the general introduction regarding the spectroscopic technique, followed by what is electromagnetic radiation, what are the various terms we will be using in this, and absorption spectroscopy, followed by UV visible spectroscopy and the applications of UV visible spectroscopy. So spectroscopy is basically defined as the study of interaction of the matter with electromagnetic radiation. So the interaction between the matter as well as with the electromagnetic radiation can be simply called as spectroscopy. And here the matter will be in the form of either atoms or molecules or ions. So matter can be either atoms or molecules or ions. And here are the specific terms which we will be encountering in the spectroscopic process. So a spectrometer is the term which is used for the instrument which is normally used to measure the presence of a particular sample molecule or a compound in the given sample. So where these spectrometers are designed in such a fashion, so where they will be measuring the responses given by the sample upon their interaction with the electromagnetic radiation. And spectrum. So this spectrum is the term which is normally given for the graphical representation. So where the responses of the sample upon its interaction with the electromagnetic radiation can be recorded in the form of a graph. So this spectrum is normally obtained in a form of graph, which is wavelength versus detector response, which will be the amount of light absorbed or emitted by the sample molecules. So absorbance versus wavelength or emission versus wavelength can be the form of a spectrum. And the most important thing is electromagnetic radiation. So electromagnetic radiation is the most important part of our spectroscopy, which is mainly interacting with the matter to obtain the final result. So this electromagnetic radiation is nothing but a form of energy which is normally present surrounding us. So where this electromagnetic radiation is nothing but our light from the universe or from our surrounding atmosphere, and this EMR is a form of energy which is known to composed of both electrical as well as magnetic components. And this electricity and magnetism were the components of this EMR, which were once thought to be they are the separate forces which have been developed by a unified theory of electromagnetism by James Clerk and Maxwell. So the electromagnetic radiation will be having both electrical component as well as magnetic component. So where both the components of this radiation will be oscillating perpendicular to each other, and also they will be perpendicular to the direction of propagation of the radiation or wave. So you can see the simple picture here. So which is showing you the form of your electromagnetic radiation. So where you can see the electrical component as well as the magnetic component and the direction of propagation of radiation. And electromagnetic spectrum. So this electromagnetic spectrum will be the term which is normally used to show the all forms of radiation together, which will be forming the entire electromagnetic radiation. So whatever the electromagnetic radiation will be having different forms of EMRs, and all these different forms of radiations together can be called as electromagnetic spectrum. And in this case of electromagnetic spectrum, we will be having radiations of different wavelengths. So where we have radiations of longer wavelengths and where we have radiations of shorter wavelengths. So the longer wavelengths radiation, so radiation with longer will be having a less frequency when compared to the radiation with having shorter wavelengths. So the wavelength of radiation and the frequency will be inversely related to each other. So as you can see here, so short wavelength radiation so here the energy of the radiation is always proportional to the frequency. So and similarly you can see here, so the shortest wavelength, so when we say the wavelength is short, then we say that the frequency is more. So which will give you that the energy will be more. So the wavelength of the radiation is inversely related to the frequency, and where the frequency is directly related to the energy of radiation. So the radiation with shorter wavelength will have more frequency, and more frequency will be having more amount of energy. And similarly we have vice versa, the radiation with shorter wave longer will be having lower frequency, which also is known to possess lower energy. And here are the various terms which we commonly use in the electromagnetic radiation studies. So we have the various terms which will be normally employed for this electromagnetic radiation. So frequency is defined as the number of waves which are produced from a source per each second, which is normally measured in terms of hertz. So frequency can be simply represented as nu, and wavelength represents the distance between two successive waves in a electromagnetic radiation, and amplitude is the maximum distance a wave extends beyond its middle position. So you can see in this picture, so where you can see the wavelength of a radiation, and you can also see the amplitude of the wave. So where the speed of the wave is given as a product of frequency and wavelength. So this electromagnetic spectrum, so which will be combining all the various forms of radiations, will be including all the radiations from shorter wavelength to the longer wavelengths. So starting from gamma rays. So gamma rays are known to have the shortest wavelength, and continuing up to the radius with the longer wavelengths. And within this electromagnetic spectrum, it also consists of a visible radiation or visible region. So where the wavelength of this visible radiation ranges from 400 to 700 nanometers. So the shorter wavelengths of a radiation will be the blue end of the spectrum, whereas the longer wavelengths will be at the red end of the spectrum. So electromagnetic spectrum contains radiations of various wavelengths starting from shorter wavelength to longer wavelength. So you can say from gamma rays to radio waves. So these gamma rays which are having the short wavelength are highly energetic in nature. So they will be having more amount of energy when compared to all other radiations. And these radiations are having the longer wavelength, so they will be having less energy when compared to all other electromagnetic radiations. So shortest wavelength will be known to have highest energy or highest frequency, and the radiation with longer wavelength will be having the less amount of energy or less frequency. And the radiation from 400 to 200 nanometer will be your ultraviolet radiation or UV region, and from 700 to 2000 nanometers will be taking it as the infrared radiation. So here is the picture which is showing you the entire electromagnetic spectrum starting from shortest wavelength to longest wavelength. So gamma rays are the radiation with the shortest wavelength, followed by X-rays, and then UV, and then visible, followed by IR, microwave, and then radio frequency radiation. So you can see in this picture, so where you can see the entire spectrum of electromagnetic radiation starting from gamma to radio frequency waves, and also you can see the picture showing you the wavelength of this radiation. So as you can see here, the wavelength is very small, which they are be having more amount of energy. And if you see here, the wavelength is more and the energy will be less. So when the wavelength is less, the energy will be more, and the wavelength is more, the energy will be less. And here also you can see here different radiations with respective wavelengths, which will also be corresponding to their energies. So gamma rays which are having very shortest wavelength are known to have highest frequency, which is responsible for their high energy. And microwaves, where you can see the longest wavelength. So where the distance between one trough and the other trough will be more, which is indicative of less energy and less frequency. And as we are discussing, this spectroscopy is mainly the study of interaction of matter with electromagnetic radiation. So what happens when such electromagnetic radiation will be interacting with the matter, which will be either in the form of molecules or atoms or ions. So here are the various types of phenomenons or kinds of phenomenon which will happen upon interaction of EMR with matter. So as you can see here, so the nature of interaction between the matter and EMR may result in any one of these phenomena, such as absorption of radiation, emission of radiation, or scattering of radiation. And this phenomenon will help us in understanding the, or will be studying the matter with respect to their qualitative purpose, with respect to their quantitative purpose. So as you can see here with this interaction of matter, so the effect of electromagnetic radiation when it is interacting on the sample matter is mainly dependent upon the energy of the electromagnetic radiation. So based upon the energy of the electromagnetic radiation which is interacting with the sample matter, the effect will be dependent. So if we take the high energetic radiation such as gamma rays or X-rays, so gamma rays followed by X-rays, so which are having more amount of energy, when they interact with the sample, they show an effect which will be an loss of electron, or we can say that ejection of electron from the sample molecules. So because of the high energy of these X-rays, when these X-rays are interacting with your sample molecules of the matter, the high energetic radiation may result in the ejection of an electron from the sample molecule. And if we see the others such as infrared radiation, they will be having a less amount of energy when compared to X-rays and UV rays, so where they are able to cause vibrations in the molecules. So X-rays being highly energetic in nature, they will be ejecting an electron from the sample, and IR radiation is having less energy than UV, they are known to cause vibrations in the molecules. So other than X-rays, if we take the UV radiation or visible radiation, so UV or visible radiation will cause electronic transitions upon their interaction with sample, whereas this IR radiation is known to cause vibrations in the sample molecule, or you can call them as vibrational changes. So high energetic radiations will be causing ejection of electrons, whereas the radiations of UV, visible and IR, which are having less energy, they are able to cause other effects on the molecule, such as electronic transitions with respect to UV and visible radiation, and vibrational transitions in case of IR radiation. So you can see here, so microwave radiation is the radiation in the EMR which is having very less amount of energy because of its high wavelength. So this microwave radiation, because of its less energy, it cannot cause, it will neither induce an electronic transition in the molecules, or neither it can cause vibrations in the molecule. So this microwave can only allow the molecules to rotate upon its interaction. So microwave radiation being the less energetic radiation will be causing rotations in the molecules. So you can see here, So UV and visible are causing electronic transitions. So where in this case you can see that the electron from ground state will be excited to an excited state. The electron which is normally present in the lower electronic energy level will be excited to the higher electronic energy level, which is in the case of absorption of UV or visible radiation. And in case of infrared radiation, the radiation which is having less energy when compared to UV or visible, it is known to cause molecular vibrations. So vibrational changes will be taking place in the sample molecules upon interaction with IR radiation. And microwave, being the less energetic radiation, will only cause rotations in the sample molecules. So based upon the effect of the radiation caused upon interaction with the matter, we can also classify the spectroscopic techniques into various categories. Whether the radiation is either scattered or emitted or absorbed by the sample. So when the matter shows absorption of radiation or emission of radiation or scattering of radiation, when it is allowed to interact with the EMR, we are categorizing the spectroscopy into three techniques. So where we have absorption spectroscopy, emission spectroscopy and scattering spectroscopy. So in case of absorption spectroscopy, the sample molecules are known to absorb radiation. So here the radiation will be either UV radiation or visible radiation, or we can say it is an IR radiation. And in case of emission radiation, again the sample molecules are known to emit the radiation. So when the sample molecules are emitting the radiation, and when we are measuring this emitted radiation, we call it as emission spectroscopy. And scattering spectroscopy is mainly seen by those sample solutions which are having particulate matter. So when the sample exists in the form of a suspension, so these particles of your sample are able to scatter the radiation upon its interaction with the EMR. So we are seeing this absorption spectroscopy. So where in case of this absorption spectroscopy, the interaction of your sample with the electromagnetic radiation results in the absorption of radiation. And because of this absorption of radiation, which means the intake of energy from the radiation, will result in the electronic transition from a lower energy level to higher energy level or to an excited state. So this absorption takes place only under a criteria or under an important condition, so where the energy of the radiation should be exactly equal to the energy difference between the energy levels. So let us say that this line, this horizontal line, represents the energy of the electronic energy level at its ground state. So GS represents the ground state of this electronic orbit or electronic level, which is denoted as E0. So E0 represents the energy of this energy level, and E1, E2. So E1 and E2 will be the higher electronic energy levels. So when the radiation is given to such sample, absorption takes place, and the electron from the ground state will be promoted to the higher energy level, such as from E0 to E1 or from E0 to E2. And the energy difference between these electronic energy levels is given as E1 minus E0 or E2 minus E0. So delta E represents the energy difference between electronic energy levels, so which is E1 minus E0 or E2 minus E0. So when this delta E value exactly matches with the energy of your incoming electromagnetic radiation, absorption process will be taking place. So H nu represents the energy of the electromagnetic radiation, so where the energy is proportional to the frequency of radiation, which is multiplied by the Planck's constant, will give you the energy of EMR. So when this EMR energy matches exactly with the energy difference between higher and lower energy level, absorption process will be taking place. And then we have this scattering spectroscopy. So where the scattering spectroscopy mainly use it to measure the physical properties of the sample. So where in this case the sample contains the solid particles or undissolved particles which have a tendency to scatter a suitable amount of light when it is allowed to pass through the sample. And the most important spectroscopy based upon this scattering phenomenon we have is Raman spectroscopy. And then we have emission spectroscopy. So where in case of emission spectroscopy, which is mainly dealing with the absorption of emitted radiation by the sample molecules. So your sample may be an ions or molecule, atoms or molecules. So when these atoms or molecules, when they are initially excited to the higher energy level, which is an unstable state, so they will be relaxing to the ground state. So during the process of relaxation, or when the molecule is coming back from excited state to the ground state, they will be losing the energy, and this energy will be lost in the form of radiation, which is called as emission of radiation. So when an electron of an molecule first excites from a ground state to the excited state by the absorption of certain form of energy. So after showing this transition, the molecule will be in an unstable state. So this is called as excited state, so which is an unstable state. And because this state is an unstable state, the electron returns, or it will come back to the ground state, and during this process it is able to emit the radiation. So whatever the energy it is taking up for this excitation process, the same amount of energy or less than that amount of energy will be released during the process of relaxation. So relaxation is nothing but the process of transition of an electron from highest electronic energy level to lowest electronic energy level, because the excited state being an unstable state. So this energy, or the energy which is emitted in the form of radiation, will be measured by the suitable spectrometer. So this absorption of the radiation can be done either by electromagnetic radiation, or we can use thermal energy in the form of flame or any other source such as plasma or laser sources. So we can use either EMR or flame in the form of thermal energy, or we can use either laser sources or plasma sources to allow the sample molecule to be in excited state, which will be the initial step in the emission spectroscopy. And once the molecule has been excited to a higher energy level, the next step will be the relaxation process, during which the radiation will be emitted from the sample, which is nothing but the loss of energy in the form of radiation. And here we have the basic principles of absorption spectroscopy. So absorption spectroscopy is mainly dealing with the measurement of radiation absorbed by the sample molecules or sample atoms. So in case of this absorption spectroscopy, we have two important laws which relate with the sample concentration and the absorption of radiation along with the path length or the distance travelled by the radiation through the sample solution. So in case of this absorption spectroscopy, the radiation or the amount of radiation which is absorbed by the sample will be measured. See, for example, let us see that. So this is your sample solution through which we are passing an radiation. So whose intensity is given as I0. So I0 represents the intensity of incident radiation which is passing through the sample solution, and then the interaction between sample molecules and radiation takes place, and the remaining amount of radiation will be transmitted from the sample cell. So I0 represents the intensity of incident light and I represents the intensity of transmitted radiation. So always the intensity of the transmitted light will be less than the intensity of incident radiation because of absorption of radiation by the sample molecules. So where we will be measuring this intensity in terms of either percentage transmittance or in terms of either absorbance. So we use either percentage transmittance or absorbance as the means of measurement of radiation absorbed by the sample molecules. So we have two important laws which provides relationship here. So if you take this Lambert's law, so Lambert's law states the relationship between the monochromatic radiation intensity when it is allowed to pass through a transparent medium, the intensity of the transmitted light decreases with respect to the thickness of the absorbing species. So the intensity of the transmitted light, so the value of I will decrease when the thickness of the sample molecules increases. So with increase in the thickness or with increase in the distance travelled by the light, the intensity of the transmitted light will be decreasing. And in case of Beer's law, so where Beer's law states that the intensity of the transmitted monochromatic radiation decreases exponentially with the concentration of the absorbing species. So where the intensity of the transmitted light decreases with increase in the concentration. So as the concentration of sample molecules increases, the absorption increases, and thereby the intensity of the transmitted light will be decreasing. And combination of these two laws is called as Beer-lamberts law. So where Beer-lamberts law states that the amount of the light absorbed by a substance which is dissolved in a fully transmitting solvent will be directly proportional to the concentration of the substance as well as the path length travelled by the radiation. So the path length is nothing but the distance of the light which is travelled in the sample solution. So this distance is called as path length, which can be denoted as B or T. And concentration represents the number of molecules in a given sample solution. So we have a equation which is given as capital A is equal to small abc, which is obtained after deriving the Beer-lamberts equation from the previous two statements. So where capital A represents the absorbance of the sample solution and B represents the path length and C represents the concentration, and small a represents the absorptivity. So as you can see here, so the absorbance is always directly proportional to the path length as well as to the concentration. So with increase in path length, absorbance increases. With increase in concentration, the absorbance increases. So A is proportional to the concentration as well as to the path length of sample cell. And this spectrophotometer is the term which is commonly used for the instrument which is able to measure the amount of radiation absorbed by the sample. And these instruments will be helpful in measuring the concentration of your solutes in the given sample based upon the amount of light absorbed by the sample molecules. So we call them as visible spectrophotometer or UV spectrophotometer, or a combination which is called as UV visible spectrophotometer. And this spectrophotometer is known to contain the basic components of a light source, a monochromator, a sample holder and a light detector. So these are the basic components which are commonly present in an UV visible spectrophotometer. So light source will be the basic component of the instrument whose purpose is to provide the electromagnetic radiation to interact with the sample matter. And the light which is obtained from the source should be a polychromatic radiation which should contain all the wavelengths of the entire range of the selected radiation. Suppose if we are choosing UV range, then the light source should be able to provide the wavelengths in between 200 to 400 nanometer. And if we are choosing a light source to produce visible radiation, then it should be able to emit the radiation which is containing the wavelengths from 400 to 800 nanometers. So the radiation source or the light source should be able to produce the entire wavelengths of the selected range of radiation. So tungsten lamp is the best example which is commonly used in the spectrophotometers for providing the visible radiation. So tungsten halogen lamp is the most commonly light source. So where it is made up of a tungsten filament which is enclosed in a glass envelope. So it is able to produce the wavelength from 330 to 900. So most of the radiation will be falling in the visible range. So these tungsten lamps are most commonly employed for the visible radiation. And then we have hydrogen or deuterium lamps which are the sources for UV radiation or in the UV range. So for ultraviolet or for the UV region, deuterium lamps or hydrogen lamps are most commonly used. So where the range of wavelength is lying from 200 to 450 nanometers. So when you compare hydrogen and deuterium, so D2 lamps are more stable when compared to hydrogen lamps, and they also offer high lifetime. So they will be having a higher lifetime, about up to 500 hours. And we also have a certain lamps called as xenon arc lamps or xenon flash lamps. So where these xenon flash lamps have the ability to emit both UV light as well as visible light. So they will be emission from 190 nanometer to 1000 nanometers, which includes both UV as well as visible radiation. And they have an advantage of that they will be having longer life periods and they will not allow the instrument to heat up, so that can reduce the warm up time of the spectrophotometer. And the second important component of the instrument is monochromator. So where this monochromator is important for the conversion of polychromatic light into monochromatic light.